Hi, in this video, we're going to talk about the explicit formula for sequences. Now, what we have here are two different functions, one on the left and one on the right, and we're going to create a table and a graph for both of them. So for the one on the left, I put that in my calculator already in my equals. I'm going to go to the table. I'm going to copy down the first few points. I'm going to pause the video and come back and do that. Okay, I have it copied. Now we're going to go to the graph and we are going to sketch a picture of the graph. Remember that when you go to the graph, you're going to want to hit zoom 6. That way we get a nice view in case we previously altered it with our calculator. So zoom 6, zoom standard, and it doesn't look like very much. I can tell you that if you do zoom out, you might get a better picture of it. So in general, to zoom out, you choose the zoom out button and you hit enter. And you can see that we're kind of sloping. If you zoom out even more, you start to actually see an exponential curve. But of course, if you do zoom 6, we're so zoomed in, it doesn't really look like much. But it does look something like this if we zoom out super duper far. Now, for the next one, we have 4x minus 1. That's certainly a lot easier to put in our calculator. We got 4x minus 1. We're going to do the same thing. We're going to go to the table. And we're going to copy down, let's say, the first 5 points. Okay, I have my points listed. And now we're going to go check out the graph. So if we take a look at the graph, I'm going to go to zoom 6 to see the normal window. And we get something that is linear. So if we were to graph this, it looks like this. Now keep in mind, these are not sequences, these are regular functions, so they are solid lines. Sequences are discrete functions, meaning we do not connect the dots. For a graph of a sequence, you would just see a bunch of dots that are not connected. Now compare the two functions to the first two examples on your homework page that you should have done before this video. And what do you actually notice? Because they do resemble what you did previously. And maybe you'll notice that you're getting some of the same answers for both of them. Because our goal is to compare sequences to functions. So on the left-hand side, what resembled your first homework question? What was happening? We were multiplying by 1.03 each time, and we got these numbers. So on the left, when you multiply by 1.03, we got something that was exponential. And on the right-hand side, what's happening here? What's the pattern? You are subtracting, you are adding 4 each time, kind of like in the second homework question you should have done. So here you are adding 4, and you got a linear function. Wow, my handwriting is bad. Okie dokie. So in functions, where did we actually see this pattern? Well, in a function, the pattern is found in the base. And in a linear function, the pattern is the slope. And that's really important. So basically, we have two different types of patterns that we can classify: addition and subtraction, and multiplication and division. So let's sum it up. for two types of sequences that we can describe are arithmetic and geometric. Now, I know it's spelled the same as arithmetic. Arithmetic is the verb. Arithmetic, what you use to describe something, is an adjective. So if you're doing 1 plus 2, that's arithmetic. But if you're describing a sequence, that's arithmetic. Now, there are other types of patterns out there, but we don't have classifications for them. So the way we're going to remember this is that A for arithmetic stands for adding. There is an adding or subtracting pattern. Now, if you have an arithmetic sequence, there is a constant rate of change, meaning we constantly changed by 4 in the last example because we kept adding 4. We call this a common difference. And we have an explicit formula that's on your reference sheet to classify these types of sequences. So let's look at the sequence first before everything gets too overwhelming. An arithmetic sequence would be 1, 3, 5, 7, 9, and so on. Can you see what I'm doing? I'm adding 2 each time. So because I'm adding 2, I would say that this is arithmetic. And I would say that my first term, a sub 1, is 1. And then my common difference, d, is 2. Because we are adding 2 each time, we say the common difference is 2. Now let's say you want to use this in a formula. You would go to your reference sheet, you would look at this explicit formula, and you would just plug in the following. A sub 1, we are starting with 1, plus n minus 1 times the common difference, which is 2. And all of a sudden, you have an explicit formula. And that's great because if you want to find the 10th term, all you have to do is plug in 10. Now, your common difference is the same as the slope of a linear function. Now, to find the common difference, you subtract backwards. So in that example I gave you before, 1, not 3, 1, 3, 5, 7, 9. If you didn't know that you were adding 2, you would just go backwards and say 9 minus 7 is 2. 7 minus 5 is 2. 5 minus 3 is 2. 3 minus 1 is 2. You get the point? Every time you subtract backwards, you keep getting 2. And you're subtracting, which is why it's called a common difference. On the right-hand side, you have geometric sequences. Geometric sequences is when you see a multiplying pattern or division. So if we are having a multiplying pattern, like on before, you have a percent rate of change. Now, I know that's hard to see, but before, when you had 1.03, the percent was you're increasing by 3% each time. Now, when we're talking about geometric sequences, we have what we call a common ratio. The common ratio is the pattern. So let's see if you have the formula 1, 2, 4, 8, 16. This is multiplying by 2, meaning we would say this is geometric. Because it's geometric, we would say that your first term is 1 and the common ratio is 2. Then if you wanted to write a formula for it, you would go to your reference sheet, you would look at the explicit formula, and you would replace a sub 1 and r. So we would have a sub n equals 1 times r, which is 2 to the n minus 1 power. And then if you wanted to find the 10th term, you would plug n as 10, and you would figure out what the 10th term is without having to repeat the pattern. Now, just know that your common ratio is the same thing as a base. And when finding the common ratio, you divide backwards. So, in other words, if we had 1, 2, 4, and 8, and so on, divide backwards. 8 divided by 4 is 2. 4 divided by 2 is 2. You want to do it at least twice to make sure you're right. Now, keep in mind that if you are dividing the way we express division, such as 10, 5, 2.5, 1.25, the way we express division is that your common ratio would be not dividing by 2, but multiplying by 1/2. Anyway, I hope this made sense. You are now going to try the next few problems on your own.